Hi, welcome to SolidCAM World Summit 2021. My name is Amod Onkar. I'm the product manager for 3-axis and 5-axis milling in SolidCAM. In this session, we are going to look at the power of simultaneous 5-axis in SolidCAM 2021. Let's begin straight away. The agenda for today's meeting are the following 3 points. First, I'm going to introduce the entire offerings of SolidCAM 2021 in simultaneous 5-axis. After that, we are going to have a live demo. In fact, we are going to make a mix between the PowerPoint presentation and the live demo of the parts that we have done in simultaneous 5-axis in SolidCAM 2021, which will show you or highlight the features and the power of SolidCAM 2021 for simultaneous 5-axis machining. And in the end, we shall summarize the entire session that we did today. Right, let's get started. So what do we have today in our offerings in SolidCAM 2021? We have generic 4 and 5-axis machining, which allows the user to machine any part in 4 and 5-axis the way he wants, with the tool axis control that he wishes to desire, with every parameter, every gouge check, and every tool axis control that's completely controlled by the user in SolidCAM. It's completely controllable. Multi-axis machining for doing roughing and finishing of prismatic pocket-shaped geometries. Multi-blade machining for machining impellers, blisks. Port machining for machining engine tubes or engine ports and tube kind of geometries. Rotary machining for machining in 4-axis roughing and finishing of 4-axis parts. Edge breaking for deburring parts in 3-axis, 4+1 and simultaneous 5-axis modes. Edge trimming for trimming vacuum form parts or parts that are made up of composite materials in aerospace. And then we have the Auto 3+2 roughing, which basically allows you to machine any part in 3+2 automatically. Roughing is completely done automatically by SolidCAM. So these are the 8 areas that we are going to see today in our session. Let's start with the generic 4 and 5-axis machining. The generic 4 and 5-axis machining has got several components in it. It's just not the generic 4-axis machining, but there are also some application-based machining that are also included in our offerings of generic 4 and 5-axis machining. So we have simultaneous 4 and 5-axis machining, Auto 3+2 roughing, rotary finishing in 4-axis, 3 to 5-axis conversion, converting HSM and turbo HSM tool parts to simultaneous 5-axis, contour 5-axis machining, multi-axis drilling, swarf machining, and geodesic machining. All of these together constitute the generic 4 and 5-axis machining in SolidCAM 2021. So we can machine any part the way we like using the generic machining. Complete control over tool axis. The user can control the tool axis and make the part move or go around on the make the machine go around the way he likes in the best possible method. User has got complete control over the tool axis. User defined gouge check, again complete control over the way gouge checks are performed. The user has a possibility to define 4 different groups for gouge check and then use these groups to make the part collision free on the machine. Smooth lead in and lead out, again completely user definable. It supports all standard tools, including the new generation circle end mills, which are the barrel tools, oval form tools, lens form tools, and the taper form tools. SolidCAM's generic 4 and 5-axis machining also supports these tools in machining any part. Exceptional surface quality, the reason here being that the machining is done directly on the surface and not on any intermediate mesh in between. So the surface quality is reproduced exceptionally in the generic 4 and 5 axis machining. Let's start with the first application based strategy that we have inside our generic, and that's the rotary finishing. Very simple one. It's designed to machine parts in 4 and 5 axis, 4 axis machine only, sorry. It can be used to machine cylindrical parts like bottle molds, cores, electrodes, jewelry rings, woodworking parts, etc. Tool paths are directly calculated on a 3D geometry and not wrapped around. It's not that you take a 3-axis or a 2.5 axis tool path and just wrap it around a cylinder. That's not done here. It's directly calculated on the 3D geometry. So there are two strategies that are available. One is the along strategy, where the tool path goes along the part, and the other one is the across geometry, where the tool path goes across the part. The best part in rotary 4-axis machining is that you can shift the tool contact point. You can have the tool not cutting exactly at the center, but an offset value from the center. Next, we move to Swarf machining, where you can see that parts like these can be easily machined using the Swarf. Now, Swarf is something that you tend to associate with straight wall surfaces that can be cut completely in one go using the side of the cutter, using the entire cutting length of the cutter. However, in Swarf machining in SolidCAM, you can also machine curved surfaces using multiple depth of cuts. It's a robust engine for machining using Swarf. Minimum inputs, all it needs is the surface to be swarfed, the bottom surface if there is any, the tool, and just the approach. The results are pretty clean because here we are directly not machining on the surface, so the small surface variations can still be taken care of, so they don't really affect the tool path, so the results are very clean. Tilt control is done automatically by the software. The user doesn't need to specify anything special for the tilt control. In fact, the number of parameters in tilt control itself is quite minimum. Almost everybody will need Swarf machining because there are paths which the user doesn't want to use multiple depth of cuts. If the walls are straight or planar walls, can be done straight away using the side of the tool, the flute of the tool, and in 1 or 2 cuts they can actually finish the part. The output in Swarf is in 3, 4, and 5 axis, so you can get the output in either of these axes. And applications basically are impellers, where you would like to do parts like these and you would like to finish them in one single tool pass. Okay, or frame components like this, where you would like to finish the walls using the frame the side of the tool, single pass or a couple of passes. Or production parts where the walls are straight or having a draft and you would like to just finish them in one go. Next is the 3 to 5 axis conversion, where we take the tool paths generated in 3 axis both in HSM as well as turbo HSM and convert these tool path into 5 axis. So it converts basically the HSM and the turbo HSM tool paths to Sim 5X. The user can actually machine deep paths using shorter tools for more stability and rigidity. So you can see in this picture, you can use really short tools, tilt the tool and go deep into the part without worrying about collisions with the other area, because the collisions are taken care by tilting the tool, by giving the tilt geometry. The SolidCAM tilts the tool, avoids collision, and is still able to machine the area effectively using the same 3-axis tool path that was generated. The process is completely automatic and with minimum user intervention. So not much of user intervention is needed in this particular toolpath strategy. When we move to multi-axis drilling, multi-axis drilling creates, it basically is using the advantage, or rather it takes the advantage of the SolidCAM hole recognition process and combines the power of simultaneous 5-axis machining or 4-axis machining and the power of SolidCAM's hold recognition, and generates what we call as a multi-axis drilling toolpath. All advanced linking, basically whatever advanced linking is there in our generic 5-axis, including the tilting, collision avoidance strategy that are there in the simultaneous 5-axis machining of SolidCAM, is available to us in multi-axis drilling. So basically it identifies all the holes on the part using the hold recognition process of SolidCAM. It identifies the vector direction of each of the hole and then machines each of the hole from that particular vector direction using the generic 5-axis engine, and thereby giving you a process called multi-axis drilling. The drill depth, because they are determined automatically by the hold recognition process, still the user has a control over the drill depth and he can modify it. For example, if the user just wants to do a center drilling, in that case he need not go all the way up to the hole depth. He can just say, I just would like to go 1 millimeter for each of these holes. So SolidCAM will identify each of the hole and just provide 1 millimeter depth into each of the holes. So the depth can be altered by the user. Then we move to contour 5-axis machining. This is a robust engine for machining just curves. No surface input geometry is needed. All the user needs to do is to provide the curves and the tool orientation via tilt lines. No surface definition is necessary. It supports different type of tools: ball nose, bull nose, taper ball nose, taper bull nose, form tools, dovetail cutters, chamfer tools. You name the tool and the tool is supported in that. And the application basically is chamfering or deburring of edges manually and trimming of parts, where this particular technology can be pretty useful. Next, we come to a very interesting operation that was introduced in SolidCAM lately. It's called geodesic machining. Basically, geodesic machining provides, in this particular toolpath engine, SolidCAM provides the next evolution in the pattern generation, field of pattern generation. You can look at the images on your right side here. You can see that the distance between the two passes or the tool paths is constantly maintained, irrespective of the direction of the tool or irrespective of the type of surface that it is cutting. So what basically SolidCAM does here is not looking at the surface from a particular direction or a particular side. Each surface is handled in a separate way, and the pattern is generated in such a way that the distance between two cuts is constant at any given point of time. So it basically uses a global distance field without a fixed direction as a reference for the engine, which enables full flexibility in terms of calculating various pattern types. We have a parallel to curve and a morph between two curves, while maintaining consistent distance between the cuts. So if you have said that I would like to have 0.5 millimeter between two tool passes, that 0.5 will be maintained right from the first pass till the end of the tool path. It works on the mesh data as well as surface groups. So we are not restricted that it needs to work only on a mesh. It can work on the mesh data, that is the solid data, as well as surfaces. Auto 3+2 roughing is another new thing that we introduced with SolidCAM 2021. And in automatic Auto 3+2 toolpath, SolidCAM creates 3+2 roughing toolpaths automatically. It basically finds the optimum direction based on the maximum stock and the material that can be machined. It analyzes, so it first finds out the first best possible mode of entry into the part. Now that particular mode can be either automatically found out by SolidCAM, or it could be user assisted, which means the user can say that my first direction of machining is from this direction. Once it knows the first direction, it generates the toolpath to the maximum extent possible and then analyzes the stock remaining, analyzes the part, and then starts determining the next direction. Once that direction is machined, it repeats this process till a time comes that no more material more than what the user defined is remaining on the part, and that's where the toolpath ends. So the 3+2 roughing can be created first by completely automatic method where no user intervention is needed. He just provides the part, the stock, the tool, the depth of cut, and the side step. Then there is a semi-automatic method in which the user provides all these things. Apart from that, he provides the first direction of entry into the part. The other directions are automatically taken by SolidCAM. And the last method is manual, in which all the vectors are provided manually by the user, and SolidCAM only generates the program or generates the toolpath from the provided directions only. It doesn't do anything else. Okay, let's look at some very nice paths that we have done using the generic 4 and 5 axis engine. So I'm going to go into SolidCAM and let's open some paths. Okay, so let's look at this part. Sorry. For example, I would like to machine this yellow colored surface here. So I have got what we call as morph between two curves, and I define or parallel to curve. So if I edit this toolpath, see that we have got morph between two boundary curves. If I look at the first curve, it's the top edge, and then I have got the bottom edge as the toolpath, as the curve, and then the surfaces that were needed to be machined. Once this is done, and once we have defined our tool axis direction, I have defined 85 degrees to the cutting direction, and this is how we end up getting our toolpath, and this is how it looks like. So this is a pretty simple part that we have seen. Let's look at an even more complex part that we can handle using simultaneous 5-axis, the generic simultaneous 5-axis engine. Let's look at this part. So here I have got a closed impeller. A closed impeller is supposed to be the most difficult part to machine. And we have not used any automated kind of a strategy for this, but we have used what we call as our generic 5-axis engine. So if I edit this toolpath, you can see that we have used morph between two curves. So if I look at the surfaces to be machined, you can see these are the surfaces that we are going to machine, the cyan colored one, and then I have got the upper curve as my start curve, and then the curve at the bottom as my end curve for machining. I'm using a tool of diameter 16. It's basically a lollipop tool, and in the tool axis control I am tilting it through a curve, and the tilt curve, if I click on show, is basically a curve up here. So I'm using a tilt curve and tilting the tool so that the tool axis always passes through this curve whenever it is cutting the surface below. So if I run the simulation here, let's go into the machine simulation. So I have the machine out here and the part, the tool and everything, and we can see how the machining happens. You can see that we used our generic 5-axis and we are cutting this part. Even if I take it more deep inside into the part, this is how it's going to look like. So if I run the simulation, this is how the simulation is going to look like. So complex parts like a closed impeller can also be done using the generic 5-axis engine. Right, let's look at some more parts in generic 5-axis that actually shows the power of SolidCAM for 5-axis machining. Let's look at a turbine blade. So I have a turbine blade here, and even a part like turbine blade can also be done using the generic 5-axis. For example, I would like to finish the blade. Now you can see that the finishing can be done in several ways. For example, I could run the machine simulation, and in this case the first finishing that I'm going to show you is with a bullnose tool. If you go to any company or any customer who's doing turbine blades, they always prefer to use bullnose tools to do the finishing. And when they are finishing using bullnose tools, they actually use not the bottom of the tool, but they tend to use the side of the tool, because that's where the RPM is and that's where the tool becomes rigid. They can use very high parameters when they're using the side of the tool here. Okay, so if I again run the simulation, if I stop it here, I can show you that the tool contact is not the center, but it's the side of the tool. Okay, and this is simply done in SolidCAM by providing a lag angle or a lead angle depending on which side you're actually cutting it. And you can see that because the surface is not straight, it's a tilted surface, SolidCAM is automatically avoiding the collision using the collision checking strategy. It machines tilts the tool in such a way that the holder is far away from the side surface. Right, so this was using the classic bullnose strategy. Then I have got another strategy out here which uses not just the bullnose, but it uses a taper ball nose in this case. So here the taper ball nose is pretty simple. It's basically using the tip of the tool to generate the machining. This is the most common method generally people use to cut parts like this using the ball nose. Again, same gouge check strategy is applied here, and you can see that the collision is avoided using the collision checking strategy that's available inside SolidCAM. Okay, these were the two tools that were currently being used for machining such parts. But of late, there is a new generation tool called as a lens form tool, where the bottom of the tool has got a pretty large radius. Thereby, you can actually take larger side steps and yet achieve the same kind of a scallop that you would achieve by taking a 16 diameter tool with a smaller step over. So basically you end up getting much lower cutting time. So I have also done the same tool path using the lens form tool. So I've got a lens form tool here at the bottom, pretty large radius, and then there is a small radius out here, so that it's a dual radius. Let's take this part somewhere at the center and then look at the simulation. So here I'm using the large radius contact and machining the part with the large radius. So it's basically using the large radius here. It's using that contact. So parts like these can also be done using the new generation lens form tool. Okay, so in generic we can use any kind of tools for machining any kind of surfaces, applying tool axis control and gouge check completely to get a collision free tool path. So a part like this can easily be done using different tools. Right, now the biggest challenge in machining such parts come when you are trying to machine the fillets, the base or the root fillets, what they call, as well as the base surface. So here I have got machining that's using a taper ball nose, and we are cutting the root fillet. So I've got a taper ball nose tool here, and I'm machining the root fillet. You can see what actually is happening in this case. In this case, if I just stop this tool path, move this on the side, you can see my B axis is been locked at 30 degrees and only the A is rotating. Now this is another very interesting thing that you could do inside the generic 5-axis. You could actually lock up one of the axes and just allow the 4th axis to keep rotating. The 5th axis can be locked and the 4th axis can continuously keep rotating around the part. A very interesting thing, and using this method you can actually cut the root fillet of such parts. So we have got root fillet here and the root fillet up here for the left hand side. Okay, that's it. That's the left hand side. Uses the same principle what we did in the earlier one. Okay, now we can also see that we can machine the base surfaces. So you can have the base surface machined using again the same taper ball nose. Okay, because this particular surface is different, that's how it machines the base. Now we could also see on the left side how it does. All these tool paths have been generated using the simultaneous 5-axis, the generic simultaneous 5-axis. So all these tool paths can be generated just by our generic 5-axis engine. Right, let's look at more paths for generic 5-axis. Okay. Let's look at this part here. In this part, what I'm going to show you is the power of collision checking of SolidCAM's generic 5-axis. You can see that I would like to machine the base surface here, but the base surface is not really visible. It's hidden by all these surfaces on the top, and we have this toolpath here that I've generated, and the collision check is automatic. Okay, when I've just defined these surfaces for my collision check, I can just click on simulate, and if I run the toolpath, this is how it's going to run. You can see that the collision checking is automatically done, and the tilts are applied automatically. The lag angle, lead angle, and the tilt are automatically applied here. This shows the power of SolidCAM's collision checking, and it gives a confidence to the user that he can perhaps machine any kind of part and not worry about the collisions really on the part. Right, let's look at more parts. Going to open more parts. Let's also look at the barrel tools. So in barrel tools, for example, I would like to show you when you're machining the blisk. Again, here I'm not using any application-based strategy, but we're using simple generic 5-axis machining strategy. For example, here I'm using the morph between two boundary curves, and these are the surfaces that I would like to cut. And I've used the upper curve and the bottom curve as my guiding curves, and the tool here is basically a oval form tool. So if I show you the tool, this is how the tool looks like. It's got two radiuses, 85 millimeter and 2 millimeter at the bottom. So it's an oval form tool. And in the tool axis control, I have said that the side tilt is along the contact point of the barrel, of the barrel shape or barrel section, and I said that the contact point should always be at 40% of the barrel shape. 0 is exactly where the small radius ends, 100 is exactly where the barrel radius ends. So 40% is somewhere in between. And this is how my toolpath effectively looks like. And when it's cutting, it's actually using the barrel contact point. So if you look, my tip contact point is somewhere here, but my actual contact point of the barrel is up here somewhere. So that's the 40% margin or range that I've given. And this again can be achieved completely using the generic 5-axis. Everything is user defined, including the contact point, and you can have bigger step downs to generate the same kind of scallop that you would generate using a 0.3 or 0.2 millimeter step down using a bigger ball nose tool. So this is how the barrel tool functions inside SolidCAM on a blisk kind of machining. I'm going to show you a similar looking blisk which was completely machined using the generic 5-axis engine. It doesn't need any special machining strategy like multi-blade or anything. Of course, it can be done using multi-blade also, but I'll show you that it can also be done using a generic 5-axis. You don't need anything special for it. Here also the entire collision checking is done by SolidCAM, and the tilts are applied automatically when it detects the collision. Okay, what happens, because this tool has a limitation, and that the limitation is the length of the tool. These are pretty deep veins or deep profiles, so it can't go completely to the final depth. So whatever is remaining, we machine it using the regular taper ball nose, which has got a pretty long length, and that can be done again using the generic 5-axis. You don't need anything special for it. So here I'm using a 12 taper ball nose with has a tip radius of 2 millimeters, and I'm just using a very small step down to machine the blades. So this can go all the way down and machine the blades, right? So this was a bit about how we handle the barrel tools. We will also look at automatic application of barrel tools for machining walls and floor a bit later. Let's move further in our generic 5-axis engine and look at some more parts. So here I'm going to look at multi-axis drilling. So I have a part here, and of course also the drill. You can see that if I edit the tool path, I've got the geometry, and if I click on show geometry, this is all the detection that it has done using the SolidCAM's feature recognition. It's found the hole and also the vector direction, and based on that, in the tool axis control, I can specify whether I want a 4-axis drilling or a 5-axis drilling, and the technology. For example, if you want a simple G81 cycle, or if you want a pecking cycle, or if you want any other cycle, G74 cycle, so you can specify your cycle, and you can also do the sorting. So you can sort how is the direction, or how the tool is going to follow the holes. It's not going to follow the way it has detected, but here it can actually follow. You can sort the direction of each of those holes, so it's actually going to number each of the holes and follow that sequence. So I've used the shortest distance. You can also use what we call as the advanced method. You can specify what kind of sorting you would like to apply, whether you would like to use a linear pattern, a circular pattern, or a cylindrical pattern. So you can define each of that. So I've used the shortest distance, and if I run the simulation, of course, please. If I run the machine simulation, you'll see that that's how it cuts the part, or that's how it drills the part. Okay, so that's the part on the table and the drill, and this is how it will do it. Again, here I've used the collision checking with the holder. Okay, so it doesn't go completely down. It's following the sequence set by the user. So we have used the shortest possible distance, so it uses the shortest distance and then machines or drills the part accordingly. Okay, let's go further and let's look at another aspect of our generic 5-axis machining. And that's a technology called as a common direction. Okay, so here I have got a very interesting situation. I have a part, I have a surface that needs to be machined, but it needs to be done in simultaneous 5-axis. But I also have a problem here that I have a clamp sitting next to it. Of course, we are not using the clamp, but the clamp is sitting next to the part. Maybe it's for some other operation that when that operation is being done, they would like to clamp, but that clamp is sitting next to the part. So if I look at the toolpath here, if that would be generated using the regular strategy of simultaneous 5-axis, this is how it would look like. It would collide into the clamp. Now, you could say that, of course, you can always give the clamp as a gouge check geometry and allow the tool to not do that, but it would become really very complex and it would generate extremely complex motions. Instead of that, what we have done is I've just copied the same operation below here, and I have provided in the collision check, I have provided the clamp as my geometry to be checked for collision. But although I have said tilt tool, I'm not going to be using this tilt tool, but what I'm going to do is I'm going to use what we call as a common direction, or SolidCAM will find the best possible direction for machining this particular surface by avoiding the collision geometry that was defined. So it's probably going to be something like a 3+2 toolpath. And exactly this is how it looks like. So if I run the simulation, you will see that it avoids the collision, it avoids the geometry that was defined for collision. It has found that this is the best possible direction for cutting the part, and you can see that it's machining the part without coming even close to the clamp that was defined. So this is a very, very interesting toolpath technology, which we call as a common direction, where you can specify your collision geometry and SolidCAM will find the best possible direction to avoid the geometry and yet machine the part. Now here it's simply 3+2. It's locked its axis of A and B or B and C at one particular angle, and it's just doing a simple 3-axis machining. Very interesting. It's a common direction machining. Let's look at the geodesic machining now. I'm going to open that part and let's look at the pattern generation using geodesic. So we have this part here, and I would like to machine this part using a single toolpath, which will start at this particular curve and it will end at this particular point out here where the spear merges. So it needs to be a single path. So earlier this was very difficult. We had to split this geometry into several paths. But now with geodesic machining, you can see that this particular toolpath can be just generated using parallel to curve, and it generates just a single toolpath with consistent step overs. So if I've specified, let's say 0.5 millimeter, it's maintaining that 0.5 millimeter all the way up to inside. So if I go into the wireframe, you can see this toolpath. That 0.5 millimeter is consistently maintained. And if I run the simulation now in the machine simulation, you'll see that all the collision check, everything is applied properly to this particular machining. So if I zoom it and start this machining, okay, so I'll just pause it and I'll move this straight to show you how the tilting happens. Now because we have used the holder, SolidCAM is sensing that it's coming close to the holder, and it's actually tilting the part in such a way that the collision doesn't happen, and then brings the part back again to its original state. So you can see that the tool is following this particular profile. The collision is completely being avoided, at the same time generating a constant step over between the two passes. So over the entire part you can actually generate the same step over, and a single tool path can be achieved. So this is the magic of geodesic machining. You can generate consistent step over on any geometry and machine any part the way you like. You can use either a regular ball nose, or you could also use the tool like lollipop cutter. Okay, we can use the lollipop tools, and this can then be machined using such tools. The principle is the same. Okay, let's move ahead. Let's look at, not this one, let's look at an HSM job that was converted from 3-axis to 5-axis. So I have got this mold insert here, and I also have what we call as, if I run this, if I take, let's say, the rest machining, let's take the most difficult one, and I'm going to unsuppress this toolpath. And if I show you this toolpath, this is a simple rest machining toolpath in 3-axis. Now what I have done is I have generated the toolpath with using no holder, and then applied the holder and converted the same toolpath into simultaneous 5-axis. So if I run the simulation, okay, let's increase the speed, and you can see that the moment the holder comes close to the part, the tilt happens. Okay, you can see that now it's here. Let's get into an area where it can actually show you the tilt. Okay, we are here, and you can see that the tool already starts tilting itself by avoiding the holder. So you can actually take any 3-axis toolpath, whether it is turbo, whether it is HSM, and you can just convert it using, for example, even if we simulate this one, this was the linear toolpath. You can take any of these toolpaths and just convert it using simultaneous 5-axis. It will take care not to touch. You can see that it keeps the distance between, so when it comes close, it tilts itself. So you can actually take any of the toolpaths like HSM or turbo HSM and convert them to 5-axis simply by providing it the tool with a holder. So you can actually use short tools to machine deep jobs if you have a 5-axis machine, and convert a simple looking 3-axis toolpath to simultaneous 5-axis toolpath, and that is done by avoiding collisions with the holder. Right, so that was about generic 5-axis. In fact, let me also just show you one final part in generic 5-axis which I could not. Let's look at the rotary. Yeah, this is the part. So when I talked about the rotary finishing, I precisely meant the paths like these which you see on your screen. It can be done using the rotary 5-axis, rotary 4-axis finishing. So for example, you have got a graphic, artistic kind of a roller that needs to be machined using SolidCAM 4-axis strategy. So you can actually machine this part like this using the rotary 4-axis machining. So it will just create a toolpath that is generated on the cylinder, but using this as the part geometry. And you can machine this, either you could go across or you can go along such paths. Right, so let's go back to our presentation and just look further. So we have the next one, which is the circle end mill support. Now, why I already showed you some parts in SolidCAM's generic using the circle end mills, but I would also like to show you some automated stuff. So we have the supports for barrel tools, oval form tools, taper form tools, and lens form tools. More and more tool manufacturers now are introducing new product line with barrel profiles, and tool manufacturers today claim and promise up to 90% reduction in their machining time when using circle end mills. SolidCAM introduced them in 2019, and we have been improving it in every version, and today we have in 2021 we have the automated toolpath generation using circle end mills, and we support barrel shapes, oval form tools, taper form tools, and lens shape tools. Now, when I said that we support it in automatic, we actually meant in multi-axis machining. So multi-axis machining basically creates a multi-axis toolpath that can be used to rough out and finish pocket shape geometries in full 5x. The user has to specify the floor, wall, and the ceiling, and the system automatically creates either roughing and finishing depending on what you have selected. Adaptive roughing features like the one shown here are also available, where it creates a constant load on the tool when still machining in full 5x. The wall and the floor finishing, as seen in this part, utilizes the new generation tools like barrel, oval form, and taper lens or lens form tools. Let's look at a part here from multi-axis machining. So I'm going to open okay, let's look at multi-axis machining. Let's look at this part here so I can show you the new generation finishing techniques that we have in SolidCAM 2021. Right, so we have a part like this here, and I would like to machine, for example, these walls here. This wall here, this wall here, and this wall here using the oval form tool. So we have got in SolidCAM in 2021, we have got the option to do wall finishing, floor finishing, or roughing in multi-axis. So we have got the wall finishing out here, in which you define the entire target as the machining area and define your flow surface. So I've defined the flow surfaces, and I also define the wall surfaces out here. Pick the tool. The tool available here are ball nose, or you can use the oval form, taper form tools for finishing the wall. So I'm using a oval form tool here. And in the tool axis control, very simple, I define the preferred contact point, and I say it can tilt to the minimum contact point, or it can maximum contact point is up to 70% of the barrel area or the shape. And the lead lag, what's the minimum. Once that is done, it generates a pretty nice looking toolpath using the oval form tool, where it maintains a constant contact, and depending on the collision geometry, it also changes the direction or it changes the tilt, but it will always have the contact point on the barrel shaped or barrel form area only and not on the tip. So using this method, I have also done for this region here. We simply have to define the floor, wall, and the machining surface, and everything else is handled by SolidCAM. Okay, and then the one in the center, that also can be done. Completely checked for collisions. Okay, now with the automated stuff, we could also machine floor geometries where we just define the wall and the floor and the machining surfaces, and the floor is automatically done. And here, when machining floor, we support two tools again. It can be either be a ball nose tool or it could be a lens form tool. Okay, so here I've used the lens form tool and it's machining the floor. Again, completely checked for collision, and we specify what region of the tool is to be used. To look at more parts in multi-axis machining, let's open this part where I can show you the tool path generated. For example, if I would like to cut this pocket here in multi-axis, I use what we call as a contouring style. So it creates a simple looking, like as if somebody has done 3-axis roughing, but again in simultaneous 5-axis. It does the entire pocket machining as if a simple 3-axis machining toolpath was taken and wrapped around this geometry. Right. In areas like this, we could also use what we call as the adaptive strategy. It has a look and feel of eye machining, where we maintain constant cutting load on the tool, uses similar principle, and we can machine this part using the adaptive strategy in full 5-axis. So parts like these can also be easily handled inside SolidCAM. Okay, let's go ahead back again to our. Then we come to the multi-blade machining. In multi-blade machining, it's a very powerful engine for machining impellers and blisks. It could have any number of blades, any number of splitters, it doesn't matter, it will machine them easily. It's the classical application is impellers with splitters, or it could be even blisks. Minimum inputs, define the surfaces, the blade surfaces and the hub surface, and the machining is done by SolidCAM. Automatic tool axis control, root fillets finishing is handled with ease. Separate strategies for roughing, blade finishing, fillet finishing, and hub finishing. Let's look quickly at the part. So let's open the multi-blade part. Right, so we have a part here. It's not simple, it's a pretty complex multi-blade part. So what you basically do is you specify which are your blades. For example, here I've specified what are my blades and which is my hub. It need not be in the same area, the hub can be somewhere else. All it needs is just a surface to recognize the hub, and this is the roughing toolpath that it generates straight away. We support ball nose, bull nose, and taper ball nose tools in roughing. In the same way, we can also perform blade finishing, and we can also do the splitter finishing. Just need to specify the blade surfaces and the hub, and it does automatically. We can also do the fillet finishing. Okay, you can also finish the fillets, and of course you can also end up finishing the hub area. This is a completely automated toolpath, not much of a user cannot control not many things inside this, but it's a completely automated system for machining multi-blade parts. If you're talking about blisks, I said that I would show you another part. Now here I've taken a blisk and I've completely done using our generic 5-axis. So blisks can also be done using the multi-blade method, or it could be done using the generic 5-axis. For example, I can take the generic 5-axis and rough out this entire blisk using a bullnose tool. Straightforward, nothing else. Okay, and then use the oval form tool to finish the blisk all the way down and finish the bottom using whatever area that is remaining using the taper ball nose tool. Okay, so parts like these can be done using multi-blade machining, or it could be done using the generic. Okay, let's move ahead. We come to port machining. Basically, it's a very powerful engine for machining engine ports or tube kind of geometries as seen here. Minimum inputs because it's an application specific machining strategy. Automatic tool access control, separate strategies for roughing, rest roughing, spiral finishing, and plunge finishing. The output can be 4 or 5 axis. Let's look at a part from port machining. So I'm going to open this. Okay, let's look at a very simple part. So I have got this part here, and if I take a section of this part, okay, keep this section here, we can see that we can do port roughing straight away. Just define the port geometry, and it machines it from one direction first, maximum possible, retracts, goes to the other area, and also machines. The user can also say that just machine from one direction or both the directions. And once that is done, you could also do the finishing using the spiral strategy from both the directions. You can see the retracts. They are not straightforward. They follow the direction of the tube when they are exiting from the profile. So this toolpath is completely checked for collisions. A slightly more complex part would look like this. Port. For example, I would like to machine the areas here, so you can see that the roughing is done in both these regions. Again, here just the geometry was defined, the tool was defined, and the roughing is automatically performed by SolidCAM. And you could also finish both of these areas. Okay, so port machining can handle such geometries. It's an application specific machining strategy, and minimum inputs, completely automated, and you get dramatic powerful results from this toolpath. Okay, let's go here. Let's go to the rotary machining. Rotary machining generates 4-axis rotary roughing and finishing toolpaths directly on the solid model. You don't need to specify anything. Parts like these can be done using the rotary machining. Rotary machining can also be applied for turbine blades to do roughing. We support 3 types of tools: bullnose, ballnose, and end mills. It works like 3-axis roughing. However, the main slicing is done in cylindrical place and not one directional. The user only has to select the part, the stock, and can rough the whole part in a single operation. Linking and collision checking is automatically done. And with 2021, we have now introduced where we can shift the axis of the tool so that the tool doesn't stay at the center when it's machining. It is shifted in either X or Y direction depending on the axis of rotation, so that you use the complete diameter of the tool for cutting, which will allow you to use higher parameters, feed rates, and RPM, and more rigid cutting. So let's look at the part here. Okay, let's go to the rotary machining. For example, parts like these can automatically be roughed out and then you can use a generic 5-axis to do the machining. For example, you can see this is how the machining would look like, and if I run the simulation, you can see it's actually trying to do kind of a 3-axis roughing, but it is done in cylindrical space, so it machines parts like this with ease. The part geometry can be anything. As long as it is rotating around an axis, it can do the roughing. And once we have done the roughing, we can use what we call as a geodesic machining here, and we can do the finishing of such parts. So you can use geodesic machining and finish these parts. You can use geodesic also and machine the floor of this particular part, and then areas like this can also be finished. Okay, let's move ahead. We go to the second last module inside SolidCAM, and that's edge breaking. It was introduced in 2021. When a part has been machined and the part is on the machine, you'll see that whenever there are straight edges or non-tangent outer surface topologies, you'll always find burr. And to remove this burr, the user either does it manually or has to generate programs which actually take the same amount of time, or probably more than he would have taken to generate the programs for machining the part, just to remove the burr. Okay, so SolidCAM's edge breaking automatically detects these edges and creates a deburring toolpath. Currently, this is a manual process. I know several of my customers do it manually, and approximately the part programming or the programming that is needed to do the deburring takes the same time as programming the part for machining. So it's a pretty long process, and this entire thing has been completely automated inside SolidCAM. It hardly takes less than a minute for part like this for it to generate a deburring toolpath, and the deburring can be done in 3-axis, in 4+1. It can be done in minimum tilting of 5-axis and also full 5-axis. Let's look at a part here which utilizes the full 5-axis when doing the edge breaking. So I have got this part here, and I use the edge breaking cycle here, and if I run the simulation, you'll see that all the linking, all the machining is done automatically. It finds the edges, it finds the regions to be machined, and then runs using the standard ball nose tool to do the edge breaking, and it removes the burr automatically without any user intervention. Parts like these can be done completely in just 1 minute. You can see the tilt also happens automatically. The tilting is done automatically by SolidCAM, and any region can be taken and machined. You can see that the regions that cannot be done in one side, it tilts and it goes into the other side when it is doing the machining, so that it doesn't create any kind of collision either with the tool or with the holder and the part. So it's a very, very powerful process, and it can machine any part. User can define the edges manually, or it can detect the edges automatically and generate the deburring toolpath. Okay, it's a very powerful process, saves a lot of time, saves a lot of manual labor on the shop floor to deburr such parts, and most importantly, it is done mathematically, so you don't end up ruining any of the edges of the part. Right, let's move and look at the last feature in our 5-axis, which is the edge trimming. Edge trimming basically is for energy efficient materials like composites, which are getting popular today in aerospace. They're generally cast, and these parts require an edge trimming operation to generate their final shape. Vacuum form parts in automotive industry also need the trimming operation to get their final parts. So SolidCAM's edge trimming is a highly automated algorithm to create an edge trimming toolpath. The trimming edge can be identified, like in edge breaking, it can be identified automatically by the user, or it could be user defined. User can say, okay, use these edges and only do the trimming of these particular edges. The position of the tool is relative to the geometry, can be defined by various options, right from a simple 3-axis output to a more complex 5-axis output with different tool axis orientations can be performed in the edge breaking. Let's look at a part with edge breaking. Okay. So I have a part here and I would like to run the tool around the edges and trim off this toolpath around the edges. So SolidCAM automatically creates a toolpath for me where it runs the toolpath around the edges, detects them, and then machines them to free the part from the actual raw part that was either cast in composite or vacuum formed in plastic. So if I run the simulation, this is how the simulation is going to look like. We can also define the axis limits so that the tilt can also be controlled. And even small holes like these are automatically done. So this toolpath is highly automated. There is very less scope for user intervention apart from defining the limits of tilt where user doesn't want it to tilt, or moving the start point around from where he would like to start and end, or he could completely define the input geometry of the edges right from the start and not use the automated route. So most of the things here in edge trimming are automated, except few things that can be controlled by the user. Right, so let's go ahead and summarize what we have seen today. So in the summary, it's a very powerful and a complete solution to machine any part in simultaneous 4 and 5 axis. It's most tested and proven engine. It's been around for the last decade and a half. So it's a very powerful engine. It's been tested around for many years. The results are reliable. The results are accurate. You get a collision-free toolpath, etc. Easy to learn and use. We have got extensive training material that we have developed over the last few years for people who would like to work with simultaneous 5-axis inside SolidCAM. Right from the most basic concepts to the most advanced things, the training material is available on our website in SolidCAM, provided you register for the same. The user has got complete control over all aspects of the toolpath. Then we also have the application-based machining strategies where things are automated. So it has got a very nice combination of user control and automation. Complete control over collision avoidance. The way you would like to control the collision, you can do that using the simultaneous 5-axis engine of SolidCAM. And then we have application-specific 5-axis machining strategies like impellers, engine ports, rotary components, aerostructures, die mold parts, swarfing, jewelry parts. All these can be done using the application-based strategies. Of course, the edge breaking and edge trimming, they complete this entire offering of simultaneous 5-axis solution that SolidCAM has today in 2021, and they add value to the entire offerings of SolidCAM 2021. Thank you very much for watching this particular presentation, and I wish you a great year ahead for 2021, a happy and a healthy year for 2021. Thank you again. Bye-bye.